My name's Johnny Rodgers. I'm an applications consultant for FG Wilson. I've worked along with Robert Breeden, who you'll hear very shortly, for almost 20 years. We work in both pre-sales with design of systems, consultant engagement, conceptual design, and also right through to in-territory. If there are issues with installations, we look at the complete application, mechanical, electrical, to ensure the best performance. What I'm going to speak about today are the mechanical considerations for generator applications. So my mechanical background, I deal with the energy that is in the system, in the energy balance, all of the mechanical aspect that is related to the output of electrical energy. So typically with diesel, high compression diesel engines, we're around 39 to 40% efficiency. So from fuel input, we'll have approximately 39% electrical kilowatt energy. So initially, this first session, we're going to speak about providing the fuel system for the energy supply, and then looking at the cooling system and how we deal with heat, discarded heat from the system. So if we assume with the energy balance, we're looking at how to provide the 100% of total energy input required to support the generator efficient function. So the fuel is being supplied for combustion to ensure that we can combust within the cylinder to rotate the engine and provide energy through to the alternator for our electrical output. We also have fuel that's supplied to the engine and returned back to the fuel tank, and that's the unburnt fuel that cycles around the fuel system. And then the quality of the fuel, the type of fuel and quality of the fuel, this directly reflects on the life of the engine and obviously the performance, how much energy we can have from the generator set. So in the supply of fuel, it's not just fuel quality, it's also what is within the fuel. So contaminants, dust, sand, also water. We can have water with diesel fuel tanks, and we have metal fuel tanks. The difference in temperature from outside air to inside the tank would be approximately 8 degrees, and you will have condensation can gather within a tank. So that can bring water into your fuel system, which would interrupt combustion. So what we do is we look at how we filter and how we arrange water separation and how we design the system to avoid that water interrupting the engine performance. The main reason is the function of how we put fuel into the cylinder before we compress and combust. We're applying fuel through injectors, typically unit injectors, and these injectors are plunging at a very high speed, high velocity, and we use the fuel to fire into the cylinder to combust, and also to go around the plunger, around the seal, and remove heat from the mechanical movement in the injector, and also to lubricate the injector. So if we have any other debris or material, that can interrupt lubrication and cause an injector to lock. And with a locked injector, that can be an extreme engine failure. So when we look at our fuel system, we typically have two basic types of fuel system. We have a direct connection where the generator and engine is directly connected to a local fuel tank. So this would be like our small mobile generators, typically. We also have systems normally for larger engines or for longer running hours, where we will have a local tank to the generator and then a bulk storage tank with additional fuel fill. In each case, the local tank always has a supply and return in every installation. A quick note when we're sizing the tanks is the autonomy, or how many hours of operation do we need. And from a basic design, if we take the kVA of the generator and divide by 4.5, that gives an approximate fuel consumption figure for most of the range of engines. So it's a quick design sizing for tank volume if we're looking at an installation. So just to look in more detail, when we're looking to size the system and to have a fuel transfer from our bulk tank to our day tank, we look at the route of the pipework. Normally, we will have to pump between bulk tank to day tank. This is a preferred way because we can control the pressure to the day tank. And when we're doing this, we will look to size this pump based on the number of bends within the pipework and the length of pipe. We do pump sizing calculation for the pressure and sizing of the pump. In that, we decide on the pipe size, so the diameter of the pipe, to ensure we have a balanced pressure at the correct fill rate for transferring. So we do these calculations. They can be provided through AFK Elektra as well. When we're designing our system, we will be designing to standards, so global standards. There are standards for particular countries. There are also, in each region, you will have relative standards for ISO, possibly UL, tank standards. There is a European standard that refers to a British standard of tank design. And then there are guidance in each country, or particularly in European member states. You will have standards for that country. And quite often within Europe, there's a standard guidance in the UK called DEFRA, and you will find this referenced through European compliance documents. Also, we see DEFRA references in Asia, across the Middle East. So with the fuel system, the standards and the compliance, they refer to three basic functions. One is a section related to storage, for fuel storage. Another then is for the distribution, so the pipework and pumping. And then we also then have to look back to engine standards for how we protect the engine to give the engines function correctly from the fuel system. So we'll touch on these in the next few slides. So firstly, with storage, we need to know how much fuel do we need to store. And basically, it's simply taking the fuel consumption of the engine, taken from a data sheet, multiplying it by the number of hours that we want to have running, and this gives us our total volume in litres. If it's a design, we may want to use a rule of thumb. There's also a rule of thumb in gallons instead of litres, depending on what territory. And this is basically, we take the kVA, divide by 20, and this will give us the number of imperial gallons, not US, but imperial gallons per hour. Another approximation. So these are rules of thumb. If you haven't finalized the generator selection, if you haven't made the exact selection of engine at specific rating yet, and you're looking at an approximate kVA rating. When sizing the tank, we have to consider allowing for additional volume within the tank. From a design perspective, it's approximately 15% additional volume. So if we need to have 1,000 litres of fuel for supply to the engine for autonomy, the tank will need to be 1,150 litres, 15%. So also we look at bonding So this is spill containment and bunding. And the bund size itself should always be a minimum of 110% of the size of the volume of the tank. And this is of the total volume of the tank. Depending on local requirements or specific applications, this bund volume may need to increase. So for example, if it's an environmentally sensitive area, maybe a fuel installation on offshore or near a river or a waterway, this bund level may need to increase by an additional 5 or 10%. And also if the bund is open to environment where there can be rainwater and you need to separate, you'll be looking at an additional 10% on the bund for that. So that'll be within local regulations, but they tend to be typical, same values. So looking at storage volumes, these vary dramatically depending on the size of the engines. So we're looking at how much fuel we're actually consuming and burning. So at 2206, 300 kVA, we're talking 100 litres per hour. With 4016, 2200 kVA, 2.2 MVA, we will be using 450 litres per hour. So it's quite a bit of a range. If you compare that to the fuel tanks in our cars or motor vehicles, the Volkswagen 1.9 litre engine that is very common, that uses around 4.4 litres per hour, give perspective, on average. And then if we look at large fuel storage, so this is one of the space shuttle tanks, solid tanks, and we're talking around 1 million kilograms of solid fuel there. So we're in a range that's very much in between. So we have particular standards for the range of engine types that we're looking to design for generator applications. The one thing that is common, no matter what the type of fuel storage, is the construction of the tanks. We're looking at metals, thickness of metal, how they're joined, and pressure. Pressure is critical in all aspects of fuel systems, and particularly in tank design. And then all of the types of tanks always have to have an access, a means of maintaining or inspecting the integrity of the tank. Here's a summary of a number of points that need to be considered and the relative reasons. So the bund, bigger than the tank, so it can take all of the volume. If the tank fractures or leaks, if there's an overfill of the tank with an alarm to signal overfill, the time delay to stop from an alarm means you need to increase the volume. If there is fire stopping in a tank room or fire protection that is injected into a tank room, that volume needs to be considered in the volume of the bund. So that's why we have to have a greater volume. When we have two tanks within the same bund, depending on the shape, size, and height, we may need to increase the volume. It's either 110% of the total volume of all fuel, or it may be 25% total capacity. It's whichever is the greater volume is what the bund size should be. And when with bunds and with drain points from bunds, this should always be into a controlled area, not down a drain, not into a waterway. All about that it can be assessed and checked when it's being emptied. I believe these slides, we'll have these available in a PDF form for you, but what we have here is this is looking at a typical schematic and some of the key functions that we need to remember why they're there. So this is the tank within an external bund, and within the bund we'll design to have leak detection. So if there's a leak into the bund, we know. We have manhole for inspection, so we can check what is in the tank and check the integrity of the tank. We've our fill line, so we need to size our fill line. And we size our fuel suction lines, so the sizes of the pipe, and that's relative to the pressure within the tank for supply and for extract. We may have a fuel return if the fuel is returning from an engine, or it could be a fuel dump from a day tank to a bulk tank. Each of these have to be sized with the sizing of the vent from the top of the tank, because as fuel goes into the tank, air must escape. As fuel leaves the tank, air must come in. And that relates, that volume, or that the area of that outlet will relate on the pressure capability of the tank. That relates to the welding of the sides of the tank and the type of tank and type of construction. There may be fill points remote. Quite often we may have a fuel tank in a basement, and we could have a fill point 120 meters away at a different level. And we look at the sizing of the fill point and alarming. We may have foot valves, and this is to protect from debris being sucked into the line. They should fill back to level gauges. Normally, when we're taking fuel from a tank, the preference is to come out the top so you can control if there is a leak. We do multiple sensors in tanks. More commonly, we will have 4 levels. So we'll have a low level when the tank is becoming low. We'll have a low level that will then stop generator, inhibit the generators, so you don't pull air into the engine and lock the engine. We'll have high level to say that the tank is full, and a high level is an alarm and shutdown to stop overfill prevention. We can have drains from the tank to remove condensation, water, and dirt, or we may have a suction drain where we suck from the top to remove the contaminants. And then these will relate to a control system, either an overall BMS or a building management system, or to the generator controller, or it can be coming out to our fill point and our fire systems. So the comms from alarms and comms from fill levels. So when we have our storage tank, we then need to transfer or move fuel from our storage tank to our day tank, our local tank. We have standard pump systems where it's a single pump between a large tank to small day tank or local tank. But quite often, or more often, we have duplex pump systems. So resilience, so we have duty and standby. So one pump can operate. If there is a fault, the other pump then will automatically begin. We can have manual priming pumps in parallel to help when initially priming a system and removing air or drawing fuel to the pump. The important thing is we will have one-way valves or non-return valves, but important point is to ensure we have isolation valves. So when there is a fault on a pump, our pump needs maintenance, we can isolate the valve and remove the pump and leave the system still primed and operating. So this is what these duplex pump kits look like. This is a typical data center pump arrangement. Just graphically, this is what it looks like with its tray. We have clearance for air intake into the motor of the pump, and then we will have a tray for collecting any drips or spills with an alarm to signal that there is a spill or a leak. So when we're looking at how to make all of these components work, we need to design the calculation for the sizing of that pump and the pipework. And these are the items we need to know. We need to know the distance of the pipe, the number of bends in the pipe, how much flow, the rate that we need to transfer flow from the bulk to day tank. Then we look at the vertical head that we have to pump to overcome. and then the number of valves, because each valve will have a resistance that we need to consider in our pressure calculation. And what we have in the calculation, we have a compromise between the size of the pump and the size of the pipe. And we calculate, based on pressure, the most practical, usable size of pump for the minimum pipe diameter that we can. So other points that are important in our system, I mentioned all of our engines will have a fuel return as well as fuel supply. That fuel, this example is 4016 at 2000 kVA. The engine will be consuming 424 litres per hour, but the pump on the engine is gear driven, so it always flows at the same speed, matched to the rotation flywheel. So we're looking at 1500 RPM pump. When it's on zero load and when it's on full load, it always has the same flow. So that flow through the engine will be 1,380 litres per hour. At maximum load, the engine will only use a third of that, 424. So we have 956 litres returning back to the tank. We have more coming back to the tank than we have been burnt in the cylinder. That fuel is used for lubrication and also to remove heat. So the fuel returning comes back hot, and we need that fuel temperature to be controlled, because if we supply fuel back to the injector at too high a temperature, the injector seal will lock and seize. So we need to use the fuel. We use fuel coolers to reduce the heat from the returning fuel, and that allows us to use all of the volume of fuel in the tank. We may, depending on location, depending on environment, we might have additional filters. We use a lot of these Racor type filters. They can be arranged in duty standby configurations where you can remove one element while the engine is continuing to run. We use these in a lot of United Nations and military applications where there are prime rated generators or base load generators, and if there's contamination or the fuel filters are needing to be changed while the engine is running, we can isolate one filter element, remove, and keep the flow through the other filters. So it keeps it running continuously. With all of these arrangements, we need to look at any spill containment. So we will have trays underneath. We contain any spill, contain any possible area of leak, and we try to signal for alarm for any leak. And again, we think of serviceability. So this is where multiple units, we can isolate, remove. We have the same with pumps. Again, it's the isolation, be able to have isolation valves. So that was fuel and how we supply all of our fuel to the unit. Now we want to look at major source of energy that's dissipated and how we control the heat from the engine and engine cooling. So when we think of engine cooling, we think about the radiator mounted on the front of the engine, but it also, we need to look at the heat that is radiated off the engine block and any heat that comes from the windings of the alternator. So typically an alternator will be 95 to 97% efficient. So the 5% of inefficiency of the alternator will be heat given off from the windings and ejected through the outlet of the alternator. This heat and this heat needs to be considered because it will come onto the radiator and onto the cooling system. So the cooling system needs to deal with that. So the main function of the cooling system is to remove heat from the engine. This is to keep the engine operating at its optimum, most efficient condition. One part of the cooling system is also to heat the engine up as quickly as possible. So we have thermostatic valves, we have control valves to keep heat in the engine when it's starting up or on low load. We need to keep the engine at high temperature to maintain efficiency and reduce engine wear. So when we have the engine up on high load and to temperature, we then need to remove the heat to keep the tolerance of all the moving components. And this is to reduce engine wear. So we also must remove the heat from the alternator and the alternator windings to maintain the efficiency of the alternator. If the alternator becomes too hot, then efficiency drops off dramatically, significantly. So looking at engine cooling, and we think of the water circuit within the engine, the important point on energy balance, and this is in all brands of engine, we need to consider the jacket water, but also the oil. The oil is cooled through the cooling circuit and oil temperature maintained through that cooling circuit. And the engine pump will pump coolant through the oil cooler, through the passages of the engine block, and then back out to the radiator. When we're sizing the cooling group and the cooling capability and airflow, we need to look at both temperature, so maximum ambient temperature, and also altitude. Some engines will start to derate maybe 2,000 meters above sea level, some from 600 meters, but the cooling group will be affected at any altitude greater than 152 meters. So normally you will not see the airflow rate will not vary significantly, so it's not a major factor, but it's something we must consider. And if you're looking at data center applications, Uptime Institute, I think there might be some discussion this afternoon, Uptime. Uptime Institute will request a rating for a data center application for any city or any area in the world, and they will ask to confirm the rating at the specific altitude of the site and at the BISRA maximum ambient recorded for the site. So there'll have to be a declaration from the manufacturer of the rating for that specific site to meet the uptime class. So when we have our sizing of our cooling group, we then have an airflow requirement, and that airflow needs to be capable of going through the radiator and the restriction of the radiator, but also anything in the enclosure or plant room. So that's our attenuators, our louvers, our ductwork. All of that means we need to have our pressure drop capability for the airflow to allow it to be packaged. In sizing all of the flow and size of the radiator, we need to look at the type of coolant we use and what percentage glycol concentration. And you will notice through all of our FG Wilson range, we have a standard glycol requirement, so more commonly known as antifreeze. So you may think you won't have a lot of frost in this area for a lot of the time, but you will see the same glycol concentration recommended for here and for hotter countries as you will for what we'll have in the UK and even Northern Europe. The reason is that the glycol is not just as an antifreeze. It's used as a stabilizing agent to stabilize the thermodynamic performance of the liquid, the coolant fluid. And this is because engines and generators, as you ramp up in load, the thermal output lags behind, and it comes behind. As the engine can drop in load, the thermal performance can still climb, can lag behind and will still be climbing. And as the engine goes up and down in load, that thermal change can be significantly higher. So what we use is glycol as a stabilizing agent to keep the lag closer together, and it means you can have a much more efficient cooling circuit. So basically, if you take a standard FG Wilson generator and put it somewhere very hot, make sure it still has the glycol concentration because it affects the cooling. So in looking at cooling, we have the water circuit, which is also cooling the oil, but all of our engines, we do not have any naturally aspirated engines any longer. All of our engines will have turbochargers. So those turbos, that turbocharged circuit, that charge air circuit needs to be cooled. So with the majority of our standard engine and generator ranges, we have what we call a TAG system, and this is turbo air cooled generator application. What we have is the blue is the water circuit, or jacket water and oil, and then we have the air coming through the compressor, and then the hot air after combustion being discharged into an air-to-air cooler. And the airflow then comes past the generator, through the charge air cooler, and then onto the jacket water circuit. So that's just how, this is the majority of our generators. We have, in the 12-cylinder range, from around 1100 kVA up to 1500 kVA. We have the option with the TWG, and this is basically the charge circuit has an intercooler mounted within the charge circuit that then discharges the heat into the jacket water circuit, and then a single core radiator is used to cool both circuits. We also have TG, which is on some of our smaller engines, and this is really where there's a higher flow through the charge circuit, and it's discharged to ambient air and to exhaust. So it's controlled through the turbo selection and turbo sizing, and the radiator core has then one single circuit. We may have heat exchanger cooling, where we're taking the heat onto another cooling source, a cooling tower, a remote radiator, maybe another form of seawater cooling. And this is where the engine primary circuits are all controlled local to the engine, and then there will be a secondary circuit of cooling source. So that'll be a low temperature circuit, and we cool through the heat exchanger arrangement. These can be on a TWG, where we have an intercooler still on the engine. We also have on the larger engines, we can have a TRG system. It can be with the heat exchanger again, or with the radiator. And what we have is another intercooler that's being cooled by that same secondary circuit. So we have two intercoolers, an intercooler that's mounted on the charge water, air to water circuit, and then a heat exchanger on the air to water secondary circuit. These different configurations give us a variety of cooling platforms to use, but in effect they all are providing the same function, and with the function we have similar options for different applications. Our standard set mounted cooling is a radiator, as we say it, maybe single circuit, or it might be a twin circuit. Then we can have heat exchanger selections, where the heat exchanger will be sized for charge and jacket waters, or charge air and jacket water. But these will be supplied as a package with the generator. And what happens is then we look at the expansion vessel, the sizing of the header tank, the deaeration lines, the venting. That's all catered for on the generator package with its remote cooler. And then there may be remote radiators to be used, so a radiator in another location from the generator. So with the cooling airflow, we need to ensure that we have sufficient airflow for the cooling of the generator and for combustion. And we have not, so on the inlet side, we will always have cooling airflow, sized for the radiator, and we add on the combustion airflow that the engine needs for combustion. These will have to come into the room or into the enclosure, and this is where we look at the sizing of a louver, a weather louver, or it can be a gravity louver. There will be a maximum velocity to avoid water ingress and based on pressure, and also we keep the velocity down to control noise, because if we have a high velocity at a louver, we can generate noise. When we're looking at applications that may have sand trap louvers or dust protection louvers, these will have a much lower maximum velocity because there will be a high pressure performance louver. And then we may have attenuation to incorporate for noise reduction, and this will also affect that cooling airflow. So we have many different types of applications. In looking at cooling, we've different arrangements of how, whether it's standard canopies, we put a standard canopy, that's its cooling group is selected, but we may have these as an array of multiple generators. So this site has 44 of these. This cooling, we need to look at how the airflow comes in and how each airflow affects the neighboring generator. So we look at how we can model that airflow performance. It might be containerized. This site has many over here? 20, we have 12 1.5 megawatt engines. 14, sorry, 1.5 megawatt, and we have to look at how the airflow can come into the container, can discharge, and how the hot air from exhaust, how that might interact in the airflow around the system. Also, how the heat affects other equipment, neighboring equipment, whether it be switchgear enclosures, these are transformers. We ensure that we have to direct where the direction of heat and the heat coming in, what other elements are contributing to heat sources around the site. And then we have more complex installations where we're looking at how to get flow into a building, into a plant room. This may involve taking air into the side, a mix of direction of airflow. Some are where we have vertical discharge, where it's combined with exhaust discharges. We look at these as applications for application support, and we do a lot of very bespoke installations, but fundamental design parameters are still the same. We just have different change of pressure and flow.